Section 9.4, radius of convergence. Let's start with this known power series that we had worked on earlier. If you remember how we got here, we did two manipulations to the geometric series. We did a manipulation maybe that u squared is equal to x. Let that filter through. And then maybe after we did that, we did another substitution, which would probably have been something like negative u squared is equal to x squared. Did another set of manipulations. This statement is not true for all x's, though. We say that this statement is only true when the infinite series on the left-hand side converges. We might say that the values of x that makes this statement an identity, something that is always true, is the values of x from -1 to +1, which was the interval of convergence for that original geometric series, the one that we started with. What we're going to do is, in this section, we're going to explore this idea of interval of convergence. We're also going to combine it with this idea that in 9.2, where we investigated Taylor series and Maclaurin series, we said that each of those series has a center. When we look at this particular series, can we pick out what the center of the series is? Zero. Okay. Because series are either written as A0, A1, X, A2, x squared, ... The power series are written in this form, or they're written in this form. A1, x minus A, A2, x minus A squared, that's an A, so on. This one we said is centered at 0. This one is centered at A, where A is some value. No. Lucy, you had your hand up.
Is it centered at the point, the midpoint of -1, 1?
Okay. It is true that the center of a series is also the center of the interval of convergence. The interval of convergence and the center of the series ends up being exactly the same thing. Yes.
Do you have a pen or pencil on me, Brian?
Sure. I got a whole one in this tin. You can always help yourself. All right. So that is absolutely a true statement. But let's make some more general statements. Oh, I'm sorry. The book wanted you to look at this graphically as well. Here's the graph of 1 over 1 plus x squared. And there's the graph of various orders of the Taylor series. And you can see that between -1 and 1, that the graphs of the Taylor polynomials are very, very similar to the graph of the original function. But let's get to the meat of the matter. It's called the Convergence Theorem for power series.
Write them down.
Yep, this is going to be write it down, and then while you're writing it down, I'm just going to make sure I explain it. We're going to make these general statements about power series, about their radius of convergence, their center of convergence, and what it all means. Statement number one. Statement number one is that if we have an interval of convergence, it has a sort of a finite interval, like from -1 to +1, that kind of thing. then we can also write that interval of convergence as a number r. We'll call that number the radius of convergence, which is being subtracted and added to our center. Now the way they write that, is x minus a is less than r. That's the way they write that. I like to think of it as an interval that goes from x minus a, the center, minus the radius of convergence, all the way up to x minus a plus the radius of convergence. But both of these things are saying the equivalent thing. We have some center at a. Oh, I'm sorry. Totally write that wrong. Let me try that again. The interval of convergence is from a minus r to a plus r. There we go. That's better. If we solve that absolute value sign, we would see that. So you've got some interval in the middle of the interval is a. From a down to the bottom of the interval is a. Down here is a minus r. From the center going up is a plus r. It creates an interval of convergence that is 2r wide. And that's the case from the previous example. Now there are two other possibilities that exist. One of them is what we encountered with the power series for e to the x, sine of x, and cosine of x. Those particular power series converge everywhere. From negative infinity to positive infinity. And the last case is every power series converges at least in one place, and that's at its center. Some power series only converge at the center. Now, what do I mean it converges at the center? Well, if I put the centering value into every location in x, I get a bunch of expressions like a minus a, or a minus a squared, or a minus a cubed. All of those expressions go to 0. The only thing that's left at the center is the value of that first term in the power series, the a naught term. So there's our three conditions, or three possibilities. A power series either is in a bounded interval from a minus r to a plus r, or it converges everywhere, or it converges only at one infinite dot. So, there's our three possibilities. Our next goal then is to say, for some series that is given to you, how do we find the interval of convergence? How do we find the radius of convergence? And for that, we've got some new things called new tests. And as soon as you're ready, I will go to the next slide. Not seeing anyone looking panicked, so I'm going to go to the next slide. One of them is something that we touched on earlier, but we're going to hit it harder right now. And it's called the Nth Term Test for Divergence. And it simply says, if we've got some expression, some infinite series from 1 to infinity of a sub n, if a sub n, if the limit of a sub n as n goes to infinity, either fails to exist or is not 0, that series must diverge. I did this example, I think the first day we did series. I said, how about the series 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. Now, this test says, hey, take the limit as n approaches infinity of exactly that. It's just 1. Is this value, does this limit exist? is it different from 0?
Yeah.
If it's different from 0, it must be divergent.
If it exists and it's different from 0.
If it doesn't exist, it's divergent. If it does exist and it's different than 0, then it's divergent.
So if it's 0, it's convergent.
No,
Should we write
that is not what this says.
down 4?
This is a test of divergence, not a test of divergence and convergence. That's the trap they set for you.
Can you do this and take one more time? Sorry. It's right there.
Okay. If the limit fails to exist or is different than 0, our conclusion is divergence. We cannot use the test for divergence to prove convergence. You just fell into the trap that almost everyone does the first time. You just fell into it quicker. All right? How about another example? How about that infinite series? What is that infinite series? Can you
It's
read?
1.
Pardon?
Oh, it's infinity. It's wait, no, we
Well,
want.
no. Give me the first 3 terms of that infinite series.
1,
1 plus 2 plus 3.
It's oh wait, that was not
The limit of the nth term,
infinity.
in this case, is infinity. Conclusion? Divergence.
Wait. Oh, but it's different from 0.
Because it's different than 0. And then, here's the other classic example. This is what? 1 minus 1 plus 1 minus 1 plus 1 minus 1.
Divergent.
Yeah, that's divergent because it doesn't ever go to a it, what's that word? It's like an A.
It's alternating.
No, alternating.
The limit of this expression that then goes to infinity does not exist. It goes back and forth between -1 and +1, -1 and +1. It never goes to a particular value. That limit does not exist. Conclusion, this series diverges. Yes, Billy?
So what happens if it does equal 0?
If it does equal 0, we say this test is inconclusive. The nth term test cannot be used to prove convergence. If it does equal 0, then we'll have to resort to some other test. It's like kind of like this. Your arm hurts. You go to the hospital. The first thing they probably do is take an x-ray. Okay, the x-ray shows that the bone's not broken. Does that prove that you have cancer then?
Yes.
From the x-ray you probably can't tell whether the pain is being caused by cancer or carpal tunnel or... All right?
Oh man.
So we use this test to prove divergence, but when it doesn't work out, when the limit is equal to 0, it is inconclusive, and we must apply some other test to figure out what's going on.
Do we always want it to be divergent? Because
Oh, we
we're
would.
always trying to find it.
Divergence are like the chocolate-covered cherries of the series world. I love it. You see, you look at them and you look at all the different series that you could solve, and the ones which have these non-existent or non-zero limits, those are the ones you grab first and you pop in your mouth. As compared to those ones with the sort of, the ones with orange rinds in them. Ew is right. Okay.
I like this one. Good analogy.
All right. So again, to hit this point home one more time, the nth term test only proves divergence. You may not use it to test for the convergence of a series. We'll have to have other tests for that. By the way, you already know one other test for this, and that is if this power series happens to be geometric, you know a way to test to see if a geometric series converges. Is the common ratio less than or equal to But the absolute value of the common ratio less than or equal to 1, or the common ratio between negative 1 and 1. Josh?
So if it's not divergent, does it have to be convergent?
No. This says
Right.
when we see particular series where the nth term doesn't go to 0, we automatically get to put the big divergence stamp on them. When we see an nth term go to 0, we don't have the convergence stamp, but rather we say, take that series and apply another test to it. All right? This by far is the easiest test, and it tells us divergence, but it's inconclusive about convergence.
Okay.
Inconclusive. All right. So what other tests do we have? Well, I mentioned we have the geometric series test, but we also have this test called the direct comparison test. Now, the direct comparison test is great when we have a series that we can compare to another known convergent or divergent series. So let's say that we have some series that it uses the terms a sub n. And all those terms in that series, by the way, are non-negative. They may be 0, or positive. We can show the a sub n series to be convergent if we can find another series, let's call it c sub n, that converges, and every single term beyond a particular point is always lower than the c sub n series. So we've got the c sub n series, it's got values, let's say 1, 1/2, 1/8, 1/4, 1/8, so on and so forth. If we knew that every single term in the a sub series was lower than the c sub n series, the a sub n series would have to also converge. We compare it to a known convergent series. Let's take the opposite case. It's kind of like a one-way sandwich.
There's no top.
It's an open-faced sandwich. Yeah, well, because they're all zero, all non-negative. Indeed, we have sort of a 0, and the c sub n is the top. So 0 could be like the bottom bread, and c sub n is the top. Because otherwise, what we have is an open-faced sandwich, but it's face down with the meat on top of the plate. That's no good. All right. The opposite case is a sub n is compared to some known divergent series. Let's call it the d sub n series. And for every value in the d sub n series beyond a particular point, the a sub n is always above it. If the d sub n series is divergent, it must mean the a sub n series must also be divergent. Either I'm stuck below a convergent series or I'm stuck above a divergent series, but whatever it is, I have to compare it to a known convergent or divergent series.
I don't understand how that proves if it's convergent or not.
It's a one-way sandwich, but the bottom bread is the origin, so you don't need.
Yeah, 0 is the bottom piece of bread. Okay, let's do a physical example of this. Your hand is the a sub n series. It's way up here. Okay, my hand is a c sub n series, and I know that if I add up all the things in my c
I
sub n.
understand the first one, I just don't understand the second.
Oh, okay. So here's my hand. It's the d sub n series, and it's below your a sub n series. Now, if I add up all the terms in my d sub n series, it goes to infinity. It diverges. D for divergence, d sub n.
Oh, then this one diverges.
And this one has to diverge too, because you're always above my known divergent series.
I thought that he was saying that it converges. Okay.
No,
Where's the big N come into play?
the big N. Okay. Very good question, Ian. Where's the big N come into play? Here's where it comes into play. Ready? Let's say this is my known divergent series. All right? And this is the a sub n series that we're trying to prove is divergent. let's say here we are at a sub 0. Wait, my divergence series is above this. Then we go to a sub 1, or n equal 1, and we may change positions. At some point, my hand gets below her questionable series. And from here on out, from this big N all the rest of the way, my hand is always below her hand.
Okay.
If there exists some N at which this is always below that, then I can show the divergence of that series. Okay, same is true on the convergent side. It doesn't mean that every single number in the series has to be convergent size. It doesn't mean that every single term has to be, of my known convergent series is bigger than that, but at least at some point I finally get above and I stay above. That point at which I am on top and I stay on top, that's the big N number.
Okay.
Alright, so let's use this new theorem to show that the series x 2n over n factorial converges. Now this is a tricky problem because it relies on something that you need to recognize and have memorized. Alright? The thing that you needed to have memorized is this. What's the series for e to the x?
Okay.
That's why you're looking at your
Let me look
notes.
through my brain here for a second.
1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th.
Okay. Now I'm going to ask something I haven't been pushing really hard, but it's really going to be more important in these last two sections. What's the general term? What's the nth term? X to the n over n factorial. Now I want you to look at the series that we're trying to evaluate. It's similar. It's the square of this.
So it's e to x.
No, you put
Just trying
x.
it out.
Don't you put x squared in? Yeah.
Okay. So we got two things going on. We got an extra square on the top, and we got an extra square on the bottom.
Wait.
Okay? I've got an idea.
Pull it out.
No. Can we quickly manipulate this original series here to create a brand new series that's x to the e to the 2x?
2 plus 2x.
Nope. Let's start with 2. Every occurrence of x gets replaced with 2x. That 1, there's no x there. 1 plus 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial dot dot dot. And this is going to be 2x to the nth over n factorial. Okay. Now, do we know that that manipulation still leads to a convergent series?
Yes. Wait a second.
It's not squared though.
Wait. This series was convergent
The bottom. This
everywhere. That was one of the attributes that we discussed when we derived that particular series.
That has
is 2n.
So this substitution conversion,
Everywhere.
also convergent everywhere. Now, I know this series converges, and it converges everywhere. How does this series compare to that series? Are they exactly the same? No. How are they different?
The bottom's larger.
The bottom's larger on this series. Wait. If I put a larger number in the denominator, what does it do to the relative scanning of those two values? The one with the larger denominator is smaller. Okay, so let me see if I can put all the pieces together. I know the series that's representing e to the 2x is a known convergent series. I know that this other series, every single denominator is bigger, making every single term smaller. What's my conclusion? My conclusion is the one with the smaller terms must be, I can't believe I misspelled convergent.
Because of the B part, right?
Convergent.
Is that one?
Yep,
D of N?
because we, no, the A part.
Alright.
We found another series in which every term is bigger than, this series that we're investigating, and the term that we compared it to was a known convergent series. That's the rigorous proof part of this slide. Would you like to know the other part?
Yeah.
The other part is the second series converges because n factorial gets it gets bigger faster than any power of x.
But I have a question.
Sure.
Because the numerator in the example is x to the 2n, and then what we solved for was x to the n and then 2x to the n. But we didn't solve for an x to anything like x to the something n. So how?
That's because I'm an idiot.
Well, what? What are we doing?
Don't blame yourself. Blame
No.
Blame the students.
Caitlin caught. Is it if you write something and it's a mistake? Is it a typo?
It's the equipment, never the player.
No, you're absolutely right, Kate. Watch. This was supposed to be x squared. All of these are supposed to be x squareds. She's saying it doesn't match. This one says 2x to the power of, but this says x to the 2n. They didn't match. She was absolutely right. It still is a manipulation. It's still, this series remains being convergent on negative infinity to infinity. So Caitlin, that was an excellent catch. Way to go.
Does that mean that the factorials are also squared or no?
No, this doesn't make these squared, but we can now compare this known series to this unknown series.
Okay.
Yeah,
So e to the x squared converges everywhere,
it sure does.
but the limit of it goes to infinity.
The limit of this expression, the limit as n approaches infinity of x to the 2n over n factorial.
No, I meant for e to the x squared.
Well, no, this is the nth term of the e to the x squared series.
Okay.
That limit is equal to 0.
N grows faster than x.
Be-
Whatever.
because for any bound x, as long as you get n factorial bigger than that x, it's going to overpower it. Now that's not conclusive proof of convergence, but it is a true statement.
Doesn't that mean it's divergent?
No, if it's not 0 or does not exist,
Oh, okay.
it's divergent.
Oh, okay. I see it now.
Okay, so that's, again, one more tool in our tool belt for showing convergence or divergence. Can we go to the next one?
I guess.
Okay, another definition. We have this definition called absolute convergence. Some series have non-positive terms. Those non-positive terms, those negative terms, actually make it easier for them to converge. If a series can still converge, even if we change every negative term into a positive term, we have a special term for that kind of series. We call it an absolutely convergent series. Or we say that series converges absolutely. If a series can still converge, even though we take out the negative signs, we say that the series converges absolutely. Here's a Venn diagram of all series. Half of the, let's say half of the series, there's a subgroup of that list of all series that are divergent. On the other half is convergent. In here, are the series that we say that are absolutely converge.
So some kind of converge, you're saying?
There are some series that converge when you have the negative signs in, but if you change all the negative signs to positive signs,
Okay.
they'll still converge. Other of them, when you change the negative size to positive size, they don't. Okay. So, now the reason why we introduced this is because in the previous example, do you remember how it said that the comparison only works when all the terms are non-negative? Which means if we had a series that had some negative values in it, we couldn't use the limit comparison test. Sorry, the comparison test. The direct comparison test, I think we call it. But what if we stripped out all the negatives and then tried to apply the comparison test? If we found that it converged, we'd say that particular function, or that particular series, converges absolutely.
What does that
And
mean?
if it doesn't, do we need another test?
Well, if it doesn't, then we need another test, yes.
What does that mean? Convergence absolutely.
Really?
What does that mean?
Just that it does converge to a number, you just don't know it.
It's like double.
This is really sad because there's like the way my other book handles it, I thought was a lot better. But the order of the new book is I can give you an example, but it's dependent upon having others' knowledge, and I can't. Like I've got one last metaphor to make here. Okay, listen. Now, the second theorem, by the way, expresses what I try to say in the Venn diagram. If I'm in the member of the set of series that are absolutely convergent, I also am in the set of convergent series. If I can prove something is absolutely convergent, I've actually shown that it's also convergent.
Because the absolutely convergent circles inside of convergent.
Exactly.
Is that because if you're adding like a negative to it, then it will get closer to zero?
It's exactly the reason why. All right. Let's continue on. So let's start with this idea. Take a look at that series. The series of sine of x to the nth power over n factorial. Does the sine of x sometimes produce negative numbers?
Yeah.
Sure. 50% of the time. And that's problematic because now I can't use the direct comparison test, right? So what I say is, you know what? Let's think of this series instead. The absolute value of the sine of x to the nth power. Let's think of that one instead. nth term goes to 0, that's great.
No, doesn't it diverge? Does it bounce back and forth between one and one?
Does it?
Oh, now
N
it
equals
becomes
0.
so now it's.
No, yeah, because that's the capacity only one one.
Yeah. Convergence.
It's not. No, it's.
You know what I'm going to say? I'm going to say that the absolute value of sine x to the nth over n factorial is always less than, or at the very most, equal to 1 over n factorial. Is that a fair statement?
Yes.
Would you say that this value is always greater than or equal to 0?
Yeah.
Would you say that this expression is always non-negative and always less than this? Yes? Great. Let me just throw another thing up here. 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, dot, dot, dot. It goes to something.
Zero.
No.
You know what that reminds me of? It reminds me of 1 over x plus over 1 factorial, x squared over 2 factorial, plus x cubed over 3 factorial. It reminds me of that when x is equal to 1. This thing is e to the x. You know what that thing is?
Either one.
E to the first. So let's put all the pieces together. The series for n equals 0 to 1 of 1 over n factorial is a known convergent series, and we know what it converges to. It converges to E. This series is always positive, always non-negative, and always less than 1 over n factorial. Which means this series must converge from the direct comparison test. This series was found by taking the absolute value of that series. Conclusion? This series must be absolutely convergent. Lastly, any series that's absolutely convergent is also convergent. Yikes! That was a very convoluted path that we had to take to get there. All right, again, this is the term from a known convergent series, so therefore, and this series, since that series converged, the series that comes from this also converges. Since this one came from taking the absolute value of that, that means that one absolutely converges. And again, anything that absolutely converges also converges. Oh my goodness. All right, let's try it again. Another slide, another test. Because maybe you can't find a good direct comparison. Here's the ratio test, and the ratio test is incredibly powerful. In fact, most times I might go and use the ratio test before any other test. Here's the idea of the ratio test. If the ratio test, you take the n plus 1 term and you divide it by the nth term. And you take the limit as n approaches infinity. You get a value L. By the way, this is only for, you have to have non-negative or positive terms. All right?
Can you do that one theorem and then do this one?
The one that we just did.
Yeah, absolutely.
Yeah, same path. All right? When you take that limit one of three things are going to happen. Either the limit L is going to be less than 1. If that happens, that means there's such a disparity between the nth term and the n minus or n plus 1 term that it's dragging it down. As it drags it down, it must mean that the series is convergent. Another possibility is that the series diverges because the top is too big. And as you take the limit, it gets bigger than 1. If that happens, the n plus 1 term is a little bit bigger than. When that happens, it leads to the conclusion that the series is divergent. The test is inconclusive if the limit's equal to 1.
This is where the golden ratio comes from.
Indeed. I wish we had time to go take that trip right now, but we don't. All right. The golden ratio. All right. So I left the rules up there, and we're going to try to apply this problem or apply this to this situation. Now, what's really cool here is that we're going to be able to use this ratio test to actually find out what values of x make this a convergent series. So here we go. If I'm going to use it on this particular series, I would say that a sub n is x to the nth over 10 to the nth. Everyone okay with that? That's the nth term. What is the n plus 1 term? Well, wherever I see an n, replace it with n plus 1. So there's our n plus 1 term. Every place I used to see an n, I replace it with n plus 1. All right, now let's get to the limit part. Take the limit as n approaches infinity of the n plus 1 term and divide that whole thing by the n term. Now, this double quadruple fraction, a fraction within a fraction, is difficult to deal with. So almost immediately my reaction is, can we rewrite this using multiply by the reciprocal, Notre Dame? N plus 1, x to the n plus 1 on top, 10 to the n plus 1 on bottom, and then I'm going to put the reciprocal of the bottom there. Now I grab my black marker because something nice is going to happen.
It becomes 10.
Wait, hold on. This 10 to the nth and this 10 to the n plus 1
This turns into
will cancel
1 over 10.
cancel out, leaving just a 1 there. Anything else? The x to the n.
Goes away and leaving it just x.
This goes away and leaves this x to the 1 power. Let me rewrite the limit now. The limit as n approaches infinity of n plus 1 over n times x over 10. What does your intuition say happens when n gets really, really large?
It'll go to
It approaches 1-ish.
This part approaches 1, which means what's left over? X over 10. So far, so good?
Yeah, but where did you get those equations? You just replaced the n with the n plus 1.
To find the n plus 1 term, every place I saw an n, I replace it with n plus 1.
So I don't really understand how you went from that and then got it, you just divided by the original.
Well, I have a fraction divided by a fraction. So that's like that top fraction
I know.
multiplied by its reciprocal.
You take that a sub n plus 1 terms and then divide it by the a sub n.
Just like that rule says. The a sub 1 term, a n sub 1 term divided by the a sub n term.
Wait, so the radius of convergence is x over time?
Well, what we find is this. You ready? If you take this expression, ready? Ready for some magic?
Yes, I like magic.
This expression, when its absolute value is less than 1, the series will converge. Let's solve that. Negative 1 is less than,
Is this lecture being recorded?
yes.
Hello, people.
Okay? I say that this function, this series will converge when x is between negative 10 and 10.
Do we even solve for L?
No, we did solve for L. This is L.
Oh,
So,
we left X is
So what's the radius of convergence here?
10.
10, because the center of this series was at 0, up to 10 and down to negative 10. The radius of convergence, which we call R, is equal to 10.
Wait, how did you get the limit as n approaches infinity of the step right before you got the x over 10? How did you split it up? Did you just split it up so n is in one fraction?
Yeah, I mean, these things are being multiplied together, so I can change their order.
Okay.
And I put them on top of each other because it's easy to see what happens when it gets big.
Okay.
Did you follow that? You ready to try it again? Let's try it again. Let's try it again. Here's a new series. N factorial x to the n. Now what was that first step I did? I wrote out what is the a sub n term. N factorial x to the n. Then I wrote out what is the n plus 1 term. Every place I saw an n, I replaced it with n plus 1. So this is n plus 1 factorial
X to the N.
times x to the n plus 1. And now I'm ready to take the limit as n approaches infinity of the n plus 1 term on top divided by the n term on bottom.
It was a lot easier than this one.
Yeah, this one's a lot easier. Any nice cancellations happen because I changed to the red pen.
Cancel X to the N and leave X just X.
Do you agree with Paul?
Yeah.
Anything else?
Do n factorials cancel?
Sure.
Then we just get 1 factorial?
No.
No.
Okay. I want to remind you that n plus 1 factorial is equal to n plus 1
Times factorial.
times n factorial.
So we put that
6 factorial is the same thing as 6
times 5.
times 5 factorial. So if I rewrite this in that form, I get n plus 1 times n factorial x over n factorial.
Oh.
So it's x times n plus 1.
Wait, why?
Why does n plus 1 factorial equal to n plus 1 times n factorial?
No, like, I don't understand what you did with n plus 1 times n factorial.
I rewrote this like this because now I would like to cancel out those 2n factorials.
Okay.
And what do I end up getting? The limit as n approaches infinity of n plus 1 times x. So if n is some finite value, as n goes to infinity, this is equal to infinity. What's our conclusion?
Wait.
Okay, Caitlin, here's what I need you to do.
This is just.
Think of x as some value variable that you set. You can set it to anything you want. You name the number.
Kind of like the number one.
The number 1. So this becomes n plus 1 times 1 as n goes to infinity.
Oh yeah. Okay. Okay. Makes sense.
Even if this is really small, 1/1,000,000.
Oh yeah. I got it. Wait. Yeah.
This value is going to overwhelm it. This goes to infinity. Guess what our conclusion is? That it diverges, except in one location. It diverges everywhere except that's with a P, at the center of this series,
0.
at x equals 0. Why? Because when we have x equals 0, we got just a chain of zeros.
Does that count as less than 0? L would be less than 0.
No, L is infinity. How is infinity less than 0?
No, if I put 0 in for x, would that count as like the
Oh yeah,
series
that the limit of that is always, yeah. Okay, I understand you now.
No, that's hard.
Charlie.
Are there any that aren't absolutely convergent and L is equal to 1?
Yes, but we haven't got one yet. Ready to try it again? In this case, since there's only one point of convergence, the radius is 0.
So the radius?
The radius of convergence for this problem is 0. Because there's only one place where it converges. Let's try it again.
Radius is going to be better. I don't know.
Well, it is. I mean, it's.
Yeah.
No. Okay, same idea. Same attack.
Wait, can we just take the limit and erase that version?
Ian? Ian's brilliant. He said, can we take the limit of this and see what is equal? Maybe we'll get lucky. Maybe this limit won't exist, or maybe this limit will be non-zero. Is it? I think that when n gets really big, this plus 1 matters squat.
Yeah.
I think that this function looks like 3/5 to the nth power when n gets really big. I think 3/5 to the nth power when n gets really big is a fraction lower than 1 to a really big power.
Yeah.
I say this is 0. And do we say, yay, it's convergent?
We got
No.
No, because it's a trap. I feel like Admiral Akbar.
Have you Lando?
You're kind of like Lando. Maria. Okay. So, the nth term test is inconclusive. All right, but Ian, it was a great thought. Because let's face it, we are lazy, and if we could get away with just doing it there, we'd like to stop right there.
Because it's the ratio, is the ratio test, is that only to find R, or is that just?
It helps us to find it. But let's just go. Ready? Let's see if we can do the ratio test of this. Excuse me. Up here, up here. Because the nth term test, which Ian was trying to apply, only can be used to prove divergence. If the limit exists and is equal to 0, the test is inconclusive. All right, so a sub n is 3n over 5n plus 1. A sub n plus 1 is 3 to the n plus 1 over 5 to the n plus 1 plus 1. The limit as n approaches infinity. Okay. I usually skip a step here.
And just write the
And I write the n plus 1 term first, and then the reciprocal of the n term. Instead of writing the really big fraction and then flipping it, I just write the n plus 1, and then I multiply it by the reciprocal of the nth term.
All the n's cancel.
Not quite. Let's focus on the let's focus on the 3 to the n. This one cancels out with everything except one of them on top. We're good there. But can we do the same thing here? No, we cannot. Because we got the plus. So let's see what we have when we rewrite it. The limit as n approaches infinity of 3 times 5 to the n plus 1 over 5 to the n plus 1 plus 1. Now I can't cancel them, but I can play the game that says what happens when n gets really, really big.
The ones don't matter.
This one, it doesn't matter.
It becomes 1 over 1, so it equals 3.
No.
Doesn't it?
You just fuck with the n plus the n plus 1.
When we get really, really large, this plus 1s don't matter. I get 5 to the n over 5 to the n plus 1. I always end up with one more 5 down below. I have effectively 3/5.
So
That's inconclusive to me.
invert.
This number is less than 1. Therefore, the limit as n approach, sorry, wrong. Therefore, the series from n equals 0 to infinity of 3n over 5n plus 1 no, not equals, is convergent.
Could you just use that rule though? Like if the top, if the end, you know those rules where if the top is bigger than the bottom, or if they're equal, could you do that in the start?
No.
No?
There is another way I could have done this problem, and it may have been, it could have been a little easier. Okay, let me please demonstrate that the ratio test is not the only way to do this problem. All right? I want to directly compare this to a known convergent series. Here's a second way to do this problem. Is that a known convergent series?
Yeah. Well, we already talked about it.
Why is this a known convergent series?
Because, well, as the n gets closer to infinity, it's going to be closer to 0.
Okay, again, you're looking like you're applying the nth term test, and that won't help us prove convergence. getting this. But yes, they get smaller.
It's e to the x.
How do I get the next term? No, it's not e to the x.
Geometric.
It's geometric! What do you mean? I start, when n is 0, this is 1. When n is 1, this is 3/5. Okay, so since the absolute value of 3/5 is less than 1, this is convergent. Okay, so there is a known convergent series. How does this series compare to that series? Doesn't that one have a denominator that's a little bit bigger? So isn't every term of this one just a little bit smaller?
So then it is still less than 1. So it's still convergent.
It's still convergent. I'm glad we got the same answer. That'd be really crappy if we did it two different ways and got two different answers. Now, which one do you get to do? Whichever you want.
I like the easier one.
I like the first one.
All right. The first, okay, Paul, the first one's mechanical. You follow the steps, and hopefully you get a limit that's not equal to 1. And you got an answer. First one is mechanical. The second one relies on you recognizing something that's similar to it, and knowing whether that thing that's similar to it is convergent or divergent. So the second way, while I didn't have to write as much, a lot's got to go up here to recognize it as something similar to something you already know. All right. Okay. This is the last slide for the 8-4 lecture, and this one is not a ratio problem. This has got a totally different spin on it. But what we're going to do is partial fractions and partial sums. Help me out, please.
A times n plus 1.
Okay, A times n plus 1 plus bn is equal to 1. Great, so far so good.
A equals 1.
Okay. Let n equal negative 1. When I do that, I get 1. That goes away, and I get b times negative 1. Oh, how many parentheses do I need? Let's try that again. B times negative 1, or B must be negative 1. What other one do you want to do? N equals 0? If n is equal to 0, I get 1 is equal to, B goes away, A equals 1. So this is equal to 1 over n minus 1 over n plus 1. Isn't that great? Great. Now let's do the partial sums part. You ready? Given this, partial sum 0, partial sum 1, because this one starts at n equals 1. Partial sum 1 is equal to 1 over 1 minus 1 over, I'm using this here, minus 1 plus 1, 2. So there's partial sum 1, the very first term. All right? Let's take a look at partial sum 2 and see if we get any insight about this. Partial sum 2 is going to be this thing, 1 minus 1/2. But now we're going to add on the second term of the series.
1 over 2 minus 1 over 3.
Plus 1 over 2 minus 1 over 3. Is that right? Mm-hmm. So when n is 2, I put like a 2 here, I get 1/2. I put 2 there, I get 1/3. Wait. Can I clean that up in a little bit? We can't. Those two go away. So it's equal to 1 minus 1/3. Great. How about partial sum 3?
How do we get that?
How do I get this step right here? Okay. The second partial sum is the first partial sum plus the next term. So here's the first partial sum right here, and I brought it down right there. Here's what I get when I put the next numbers in here. When n is 2, I get a 1 over 2. When n is 2, n plus 1 is 3. All right. So what's the third partial sum going to be?
1 minus 1/4.
1 minus 1/4. Oh, you're going to say 1 minus 1/3 plus 1/3 minus 1/4. The 1/3s cancel out. Guess what? Guess what the nth partial sum is going to be?
1 minus 1 over n plus 1.
1 minus 1 over n.
Plus 1. It's like 1 minus 1/4 for S3.
Oh,
Silly goose.
indeed.
Which is what we had.
Great. Okay, last piece. If the nth partial sum is 1 minus 1 over n plus 1, the sum of the series is the limit as n approaches infinity of the nth partial sum. Oops. I wrote that wrong. Again. Let me try again. The limit as n approaches infinity of 1 minus 1 n plus 1. Conclusion. That series converge. And it converges to that.
Oh, we didn't do this.
We didn't have to do the ratio test. We didn't have to use the comparison test.
Many tests.
Indeed.
What test did we use the n?
No, we used the definition of the sum.
Oh.
The definition of the sum of the series is the value of the partial sum as n goes to infinity.
Let's go sledding.
Snowball.
I can remember.
You know, there's a song.
It snows after the ski test. Can we have a snowball fight?
Every year.
Shows on the AT test that after you get done with the AT exam, you can have yourself a fight. All right.
Oh, yeah.
Okay. So there's your assignment.
Hey, Mrs. Fredo, I have Passover. I can't do this. I actually have Passover too.
No, you don't, Paul.
Yeah, I
He's coming
do.
to my Seder, though. Ha.
Don't believe that.
Yeah, I gotta do Jewish stuff.
You have work today, Paul.
Shut up, loser.
I won't be here next class.
Okay, I'll record it. I'll put it up.
It's fashion show. How many people are not gonna be here? Everyone.